Hi, welcome back to part 2 of chapter 11, complex numbers. So, from the previous video, we basically covered how you would perform all the operations on complex numbers and how you would break down your complex number in terms of the real part and the imaginary part and so on. So, we also look at, for example, how you would solve a quadratic equation if a pair of complex roots are given. So in this particular video, we will first go through the idea of complex plane. So basically, complex plane is a way for us to illustrate complex numbers. So let's say we have z equals to x plus iy. So you will notice that this is very much similar to how you would draw your xy coordinates. But now your x will be the real part of your complex number. Your y will be your imaginary part of your complex numbers. So then, let's say over here, this is x, y. So this particular point here tells you where's your point z, okay? So now there is a more convenient way for us to represent a complex number. So this particular way is what we call as the modulus argument form. So the way for us to represent complex number in the modulus argument form is to consider this particular complex number on your xy plane as something like a triangle. So over here you will have x for your So over here you will have x, and then over here you have y, and this makes some angle theta. So this particular length we would denote it as r. It will be useful later on. So r would be also what we call as the modulus. So this is the modulus of z, and this is given by the square root of x squared plus y squared based on Pythagoras theorem. And then we need to take note that your r has to be positive. So the second part is the theta. So we denote that as the argument of z. So this is argument. So the argument of z basically is the angle itself. So this is given by the inverse tangent of y divided by x. But because we know that angles basically you can, if let's say you consider 2 pi radian, so you can have 2 angles or 3 to 4 angles that maps to the same particular argument. So what we do here is to fix the principal, what we call as the principal argument. We fix it to be minus pi to pi. You can also fix it from 0 to 2 pi. That's up to you. But usually in A level, we fix it from minus pi to pi. So this is the first thing that you need to take note of. Second thing is whenever you want to identify your arguments, you need to be careful. It is better if you can draw the diagram to identify the principal argument. So why do we need to do that? Because if you don't draw the diagrams, so let's say your point is over here. Because we already defined the principal argument is from minus pi to pi. So if you directly just calculate your inverse tangent of y divided by x, this will be the angle that you find. And you won't be able to, sorry, it's not impossible to do it, but it will be quite confusing if you don't draw the diagram to find out what is the principal angle. So in this case, this particular angle already exceeds pi, right? So what we need to do is to turn in the negative direction, and then we know that this particular angle will be less than minus pi, for example. So this is why you need to draw the diagram if you can't really imagine where would your complex number be. So before we go into the examples, we can also consider, for example, the polar form. So this will be what we call as the modulus argument form, whereby we find the modulus and we find the argument. We can further simplify it into the polar form. Or sometimes it is called the exponential form. By considering one very important formula, which is ei theta is equals to cos theta plus I sine theta. So why is that so? If you look at your diagram, which I draw here, so this is the real part of z, this is the imaginary part of z. So right now we have this particular, sorry, let me draw it in a better way. So right now we have this particular point x and y. So we know that here is x, here is y, and this is theta. So for example, if we denote this particular length as r instead of square root of x squared plus y squared, so you can find that r is just your x cos theta. Sorry. I get it wrong. So x is equals to r cos theta. Whereas for y, it will be r sine theta, right? So initially we write z equals to x plus iy. So x will be r cos theta, and then your y will be r sine theta. So we can basically factor out the r and leave out with cos plus I sine theta. So this is the part where it is useful to use this particular formula to allow us to write r e I theta. Of course, your theta will be your argument of z, and you need to remind yourself that this ranges from minus pi to pi. And then your r has to be positive. So this is what we call as the polar form or the exponential form. So now your r and theta is what we call as the polar coordinates. So now let's do some exercise to convert from the usual x plus iy form into the polar form and so on. So let's look at these 4 examples. So find the modulus, argument, form of the following. So A will be 8 plus 15i. B would be minus 12 plus 5i. C would be minus 9 minus 40i. D would be 60 minus 11i. So you can see that I specifically picked these 4 examples because 8 plus 15i will be in your first quadrant. Minus 12 plus 5i will be in your second quadrant. Minus 9 minus 40i will be in your third quadrant. And finally, 60 minus 11i will be in your fourth quadrant. So pay close attention to how I would calculate the argument from minus pi to pi. So let's start from the very beginning. So A. I denote U1 equals to 8 plus 15i. So the modulus of U1 will be square root of x squared plus 15 squared. So this is just 17. The argument of U1 will be the inverse tangent of 15 divided by 8. So you calculate this using radian. So in the end, you would get around 1.08 radian. So this is less than pi. So we just accept it as it is. Okay. So roughly speaking, this will be U1. So from minus pi to pi, meaning you turn around here and you turn around here. So in this case, we can just use the positive angle. So now let's look at B, which is U2 equals to minus 12 plus 5i. So similarly, the modulus form, by the way, we might as well just write down the polar form. So in this case, you just write 17 E 1.08i, for example. So that will be your U1. So let's continue with U2, which is minus 12 plus 5i. So in this case, the modulus of U2 will be square root of 12 square plus 5 square, which is 13. The argument of U2 will be the inverse tangent of 5 over 12. So, okay, so in this case, because your 12 is a minus sign, so let's put the minus sign in. So we know that the tangent is negative. So you have A, S, T, C. We know that tangent is negative when it is in the second quadrant and the fourth quadrant. The reason why you need to draw the diagram is to identify whether your angle belongs to the second quadrant or the fourth quadrant if you can't imagine it. Because it depends on which quadrant your argument falls in. This particular angle that you calculate will be different. So as we have seen before, or rather as I previewed before, The second example falls into the second quadrant. So this is U2. Alright. So we know that this is in the second quadrant. And if you turn anti-clockwise, which is a positive direction of your angle, then basically you won't reach more than pi yet. So that's why over here, what is the expression? You use your calculator to find what is the inverse tangent of 5 divided by 12. And then you use 180 minus that particular answer, which is 0.3948. So this value comes from the inverse tangent of 5 over 12. So this is how you would calculate your angle in your second quadrant. And you will get 2.75 radian as your answer. So in the polar form, this will be 13 E 2.75 I. So now let's look at the third example, which is we denote as U3. So it's minus 9 minus 40 I. So definitely we know that this is in the third quadrant. You can plot it out. So this will be minus 9 minus 40. So if you turn anti-clockwise, it will be more than pi. So what you need to do is to turn anti-clockwise based on our definition. Okay, so that's what we will do. So the modulus of U3, 9 square plus 40 square, that will give you 41. Now let's look at the argument of U3. This will be the inverse tangent of 40 divided by 9. Okay, so we know that this particular argument will be in the third quadrant. So how would you find out what is the value of the third quadrant? So basically you use pi minus out 1.3495. So this value is the inverse tangent of 40 divided by 9. But since you are turning clockwise, you need to put a minus sign. So the final answer will be minus 1.79 radian. So then your U3 would be 41 E minus 1.79 I. Okay. So now the last one, which is D. So let U4 to be 60 minus 11i. The modulus of U4 will be square root of 60 square plus 11 square, which is 61. The argument of U4 will be the inverse tangent of minus 11 over 60. So we know that this would be 60, 11. Here, that will be your angle. So in this case, it will be just the minus of your inverse tangent 11 over 60, which is minus 0.181 radian. So then your U4 can be written as 61 E minus 0.181 I. Okay, so that's how we find the polar form or the modulus and the arguments by drawing the diagram and so on. So now let's consider something more interesting. let's say I add in 2 more questions. So I already defined this as U1, this is U2, this is U3, this is U4. So let's do a multiplication of U1 with U2, and then let's do one division, U3 divided by U4. So this will be E. E is U1 multiplied with U2. So of course you can do this. So we know U1 is 8 plus 15i. And U2 will be minus 12 plus 5i. So you can just multiply everything inside. So let me bring my calculator out. So that will be minus 12 times 8 minus 96 40i minus 180i minus 75. So what you will have is minus 171 and minus 140. Okay. So now I will show you 2 ways. So basically what I want to show is, because we already know that if you write in terms of x plus iy, you can do the multiplication as follows. And then if you want to convert into the polar form, then basically you can start from here to find the modulus of u1, u2. That will give you 171 square, 140 square. So this will be 221. And then you can find the argument of u1, u2, which is the inverse tangent of 140, 171. So this is in the 3rd quadrant. So that's why when you do something in the 3rd quadrant, you need to do this. So you will need to write minus pi minus 0.686. So this will give you minus 2.46 radian. So if you do the multiplication using x plus iy, and then the other one would be a plus bi, for example, then you convert after you perform the calculation, you will get this answer. So in this particular way, what you would get, let's say the resultant complex number in terms of the polar form will be 221e minus 2.46i. Alright? Okay, so now let's do the other way around. Let's say we already know you want to be 17 e 1.08i. U2 we already know it is 13 e 2.75i. Okay, So can we make use of this to quickly find out what is U1 multiplied with U2? So U1 multiplied with U2 would be 13 times 17 E 2.75 plus 1.08 I. Okay. So after you do the multiplication, you find that this is 2 to 1 indeed. But there is a problem. You get 3.83 I. And this particular angle exceeded pi. So now what should we do? So we know that okay, so this is in the third quadrant. So we know that this is the angle. If you turn counterclockwise, it is more than pi radian. So what you would need to do is to turn clockwise, and this particular angle will be less than minus pi. So over here, you have 2 to 1 E. So I write I in front. So what you will need to do is actually using 2 pi minus 3.83. But that's not what you need to do. Because when you use 2 pi minus 3.83, yes, you find this particular angle that you want. But you also need to reverse the direction to clockwise, and that gives you a minus sign. Okay? So 2 pi minus 3.83. In the end, you will get 221 E minus 2.45 I. So there is some rounding errors because I round it twice. The first one over here, the second one over here. But this is basically the same answer as the above. So when you use the polar form to perform multiplication or division, you need to be careful about this particular angle, because remember, your principal argument is between minus pi to pi. So that's why when you see that this exceeds pi, for example, you need to convert it to the minus pi version. So similarly, let's look at f, which is u3 divided by u4. So I won't bother going into this particular method because this method, basically you can do it yourself. But what I would do is to directly make use of the u3 form and u4 form. So u3 is 41e minus 1.79i. And u4 is 61e minus 0.181i. So then you will have, say, 41 divided by 61 e minus 1.79i. So this minus, because of the division, it becomes plus. So finally, let's say you want to calculate everything out, you will get 0.672 e minus 1.61 I. So that will be your polar form for u3 divided by u4. So let's look at some other examples. So if you have a complex number, So you have complex number z, which can be further broken down into a plus bi. So if let's say you are given that modulus z is equals to 5, the argument of z is equals to pi over 6. So then you need to find a and b. So in this case, what you would need to do is to write down step by step. So z equals to a plus bi. So the modulus of z will be square root of a square plus b square, which is equals to 5. Or in other words, a square plus b square will be equals to 25. So that will be your first equation. Second equation, the argument of z is given by the inverse tangent of b divided by a, and this is pi over 6. So in other words, b divided by a will be the tangent of pi over 6, and we can calculate that. This will give you square root 3 divided by 3. Or in other words, 3b will be equals to square root 3 of a, or you can write a square equals to 3b square. So that will be our second equation. So then, coming from the first equation, 4b, okay. So the first equation is a square plus b square. So you have 3b square plus b square equals to 25. So 4b square equals to 25. So b will be equals to 5 over 2. Okay. So here's a question. Let me write down the steps more carefully. So b square will be 25 over 4. And b, if you take the square root, it should be plus or minus 5 over 2, right? So let's taking the plus or minus sign for the moment, and then substitute back into a. So a square equals to 3 times 25 over 4. So a square, the square root of a will be plus or minus 5 over 2 times with square root 3. So should we take the plus part or the minus part? So the question would be, should we take the positive part or the negative part? To answer this part of questions, you need to look back at your argument. Obviously, pi over 6 is in first quadrant. And we know that, for example, in your first quadrant, pi over 6. So your a has to be positive, your b also has to be positive. Therefore, you need to reject the negative part, and a will be equals to 5 square root 3 over 2. B will be equals to 5 over 2. So this is something that you need to be careful. You need to look at the argument and figure out which quadrant your complex number will be in. And then finally decide which part you need to take. Okay? So let's look at the final example of the day. Okay, given that z equals to r cos theta plus I sine theta. So show that z square is r square. Sorry, perhaps it's better I write here. So you need to show that z square equals to r square cos 2 theta plus I sine 2 theta. So essentially there are two ways of showing it. So I'm doing both ways, and let's denote this as the first method. So the second method is very useful to generalize it later on. So you will see. So the first method, just take what is given. Basically you square r cos theta plus I sine theta. You square this thing, so you will get r square, and then when you square the insides you will get cos square theta plus 2I cos theta sine theta plus I square sine square theta, right? So you have r square cos square theta minus sine square theta plus I 2 sine theta cos theta. So this will be your double angle formula, which is why in the end you can write cos 2 theta plus I sine 2 theta. So you show it. Second method, which is a little bit not exactly given by the question. So the question asks you to assume this: z equals to r cos theta plus I sine theta. So previously we also know that this is just r e I theta, right? So if you square this, essentially what you are doing is squaring everything on top. Okay, so this is faster actually. So then you re-expand back. So okay, so I 2 theta. So this will be just cos 2 theta plus I sine 2 theta. That's why you can directly write this. So this way is slightly more elegant to prove what you need to show. And in fact, using this particular method, you can show that if let's say your complex number is being powered to some n power, this is essentially the same as r to the power of n cos n theta plus I sine n theta. So why this is the case? Because you can start from z equals to r e I theta. When you power to, so this is what we want to show. So when you power the z to the power n, so essentially you have r power n e I n theta. So expand this, e I n theta will be equals to cos n theta plus I sine tan theta. So this would be Rn cos n theta plus I sine n theta. So it's a very fun kind of proof to show this particular expression. Okay, I think we can stop for now, and we will continue tomorrow on other parts of the chapter. See you.